Good day, viewers. Today we are going to look into a topic, electromagnetism. So electromagnetism is nothing but interaction between the electric field and the magnetic field. So when the electric field and the magnetic field superimposed, there will be a force that will be created as a result of the interaction of the both forces of the both field. Of course, you know field is a force. Now, let's think about a moving charge. As we know from Heinz Oersted, that every moving charge constitutes a magnetic field around it. Now let's just say that we have a moving charge. Now this moving charge with concentric magnetic field around it now enters another magnetic field. There will be an interaction that will constitute production of what? Force, which the magnitude of that force can be calculated. Now, we have a charge. Let's say this is a charge Q. Now, this charge is surrounded by magnetic field because in motion. Once it is at rest, there will be nothing like magnetic field surrounding it. But once in motion, there must be what? There must be a magnetic field around it. So, if this charge accelerates with a speed v, now enters another field, the external field. Maybe we have the external field here north, maybe here south. Then the field runs from north to south. Of course, you know that it runs from north to south. Now, the moment it enters this very field, now there will be an interaction between the magnetic field around the charges and the magnetic field generated by permanent magnets. Now, the force created as a result of interaction could be measured using this very formula. We have BQV sine theta. Now, B is the magnitude of the magnetic field strength. That's the size of magnetic field strength. Of course, we know lines of field, these lines are used to represent the field itself. So the higher the lines of field, the higher the what? The strength of that very field. Now, Q is the charge, the magnitude of the charge itself. So the higher the magnitude of the charge, the higher the force that will be produced. Then V is the speed at which the charge accelerates into the field. So if the speed is as much, then there will be what? A large force that will be generated. Then theta is the angle at which this very charge enters the field. It might enter with an angle of 90, below 90, 0. So think about the theta being equal to 0. If theta is equal to 0, then we are going to get F equal to B Q V sine 0. And the sine 0 will automatically give you what? 0. Multiply it by this, you are getting F equal to 0 Newton. So this is regarded as the minimum force. So this force entails that the field is, in fact, does not enter the field. It simply means it is parallel to the field. That very charge is parallel to the field. So it's either it moves parallel in this very direction or towards this direction, but the fact remains, it does not enter the field. Even if it enters the field, it does not cross the field. It does not cut the magnetic field. That means it is parallel. It just moves parallel. So it has no interaction. Simple. But if the theta is 90 degrees, then we are going to have this very force. BQV sine 90 degrees. Of course, you know sine 90 degrees is equal to 1. So that 1 gives us a maximum force. We call it F max, BQV. So that's the maximum force you can generate with this. Now think of charges moving through a conductor. We call it current because current is a flow of charges. Now, if we have this very field now, here is north and the south, we have the field. So we have this. Then if we have a conductor, and the part that enters the field is this region. This is the region that enters the field. The region that enters the field. Let's say the region is point AB. So we can now say that AB is the length of the conductor that enters the field. Now, if you connect this very conductor, let's say you connect it, if you connect the conductor to external electric source, let's say we have this, that is external electric force, maybe you may have DC source or AC source, whichever. Now, the conductor itself will now have what? A magnetic field around it, because there are charges that are moving through the conductor. So the moment the current passes through this very conductor, what happens? There will be magnetic field around that very conductor. That's the concentric field, like this concentric field. And that concentric field around this conductor will interact with the permanent magnetic field. And that interaction will constitute a force. And the magnitude of that force can as well be calculated. We have the magnitude of the force, which BIL sine theta. So at this very point, the force of attraction or repulsion, that's the force on this very conductor, which will either push the conductor downward or upward. That very force is equal to B, which is magnetic field strength. That's the strength of the magnet. Then we have the current passing through the conductor. Then we have the length of the conductor. So the length of the conductor inside the magnetic field, not all the conductor, but only the ones that has interaction with the magnetic field. So sine of angle between the magnetic field and the conductor, look at. We have an acute angle here. At this very point, we have a field. Then we have the conductor. There is an angle, acute angle here, the angle between the direction of the conductor and the magnetic field. That very angle is measured. Now, if this angle between the field's direction and the direction of the conductor, if it is 0, then you are going to have minimum force. So if it is 0, we have what? Minimum force. So we now say that minimum force now is what? BIL sine 0, where we have the theta to be equal to 0. And sine 0 will give you what? 0. So if you multiply this, you now have that minimum force now becomes what? 0 Newton. Now, if you want to get the maximum force, if you want to generate the maximum force, with the idea of this, you see that it needs to be passed. The interaction needs to occur at an angle of 90 degrees. That means when theta is 90 degrees, you have BIL sine 90 degrees. So sine 90 degrees is equal to what? 1. So hence you are going to get what? Maximum force, which is BIL. You have a maximum force. Now, as we know, force is a vector quantity. And as a vector quantity, it does not has only magnitude. It also has what? Direction. Then how do we get the direction of that very force? How will that force affect this very conductor? What will be the direction or the motion of that very conductor? So it is the force that will determine the direction of the motion of the conductor, because we know that motion depends on force. So the direction of motion is the direction of force. Now, for us to get the direction of this very force, then we have to apply Fleming's left-hand rule. Fleming's left hand. This is left hand. Now, what does this Fleming's left hand rule talks about? Now, the Fleming's now says that if your first three fingers are mutually other, if they are mutually at angle 90 degrees to each other, your first three fingers, such that the middle finger points to the direction of the field. The middle finger is the forefinger or the index finger. It points to the direction of the field. Then the middle finger points to the direction of the current. Now the thumb will point to the direction of the force, which is the motion, the direction of the motion, the direction of the force. So as we have the conductor, if the conductor carrying current, now we have the direction of current. As the current, while the current is moving in this way, field is moving downward. So you see the thumb points towards the page, towards the board. So meaning that the conductor will be pushed towards the board. If you change the direction of the field such that the lines of field moves upwards, then you change the direction. If the field is moving upward, this is the field. We have it moving upward. Then here is the what? The current. The current moves towards this. That means you have the what? The thumb moving upward. And the thumb shows the what? The direction of motion of this very conductor. Okay, let's just see its application in motor, so that you see how the thing is being applied. Now, take for example, we have a motor, electrical motor. Of course, we have a coil. We have a coil. We have a coil. Now, this very coil of wire, at these very points, now it will be attached to commutator. Or we call it split ring. For DC, if it is AC, we have slip ring. So we have this as a commutator. Then, fixed at brush, we have a brush. Fixed at brush, so we have this as brush. Now, from the brush, we connect a battery or electric source. Now, when this current enters the brush, from the brush, we have here as brush, right? The same thing here, brush. We have here split ring, or you call it commutator. Split ring, or you call it commutator. The same thing is applicable here. Now, when the current, this is the DC source now, when the current enters here, then what will happen? You are going to see, this is the direction of the current here. On getting here, the current moves in this very way. So the current here is moving upward in this very part of conductor. It moves downward in this very part of conductor. So the current moves in this way continuously. The current moves. You see how the current moves. Now, remember, whenever current moves through a conductor, magnetic field is created, which means there is what? Concentric what? Field. Concentric magnetic field around that very conductor. Now, if you have an external magnet, maybe we have a magnet here. If we have an external magnet, maybe here is north, and we have this, then here is south. So the field will now move from north towards south. The field moves from north towards south. So as the field moves from north towards south, this magnetic field of this magnet will now interact with the field of the conductor, and that constitutes a force. And we said that the force on that very conductor is measured or calculated using this. Now, the direction of this conductor, whether the conductor will oscillate in this way, clockwise or anti-clockwise, depends on the direction of current and can be measured or can be dictated using Fleming's what? Left hand rule. Now let's see the motion of this very what? Conductor. Now, at this very point, for example, when the current enters, then the current is moving upward. Now, while the field is moving in this direction, now we have our first fingers of the left hand from Fleming's left hand rule. Now, this has to point towards the field. It has to point towards the field. Now, while this middle finger has to point towards the current, a current is moving upward, not downward. So I have to change the direction so that it moves upward. So as it moves upward, while the field moves in this direction, then you now see the thumb. The thumb is moving or pointing towards the board. It's pointing towards the board. So in that case, we say that the direction is in, moving inside the board. So this one is moving inside the board. So the conductor here moves inside the board. Then what happens to this very part of the conductor? So at this very point, we have the current moving downward. Then we have to position our hands again. Then the current is moving downward. Look at the middle finger. It points to the direction of the current. Then this forefinger points to the direction of the field. And the field is moving like this. So it points to the direction of the field. The current points downwards. Field forward. While the thumb points away from the board, outward. So that outward motion shows that the conductor of this part comes out from the board. So as the conductor here moves outward, the part here moves downward. You now see that the motion of the conductor will be like this. It will be like this. So soon you see it moving clockwise. So this is the principle of what? DC motor. Remember, if you change this split ring with slip ring, it becomes AC motor. But here now, it shows DC motor. DC motor has what? Split ring, while AC motor has slip ring. So, with this very idea, I think we will continue with calculation. So you check our next video. Thank you.